Thank you, John, and for the amazing talks before.
Just 1 second. We want global streaming. Go.
Thank you, John, for the introduction and for the amazing talks before. As John mentioned, this is on the applied side of ZK proof systems. And I'm from JPMorgan Chase from London in the Department of Global Technology Applied Research under Marco Pistoia. And we are looking on how we can bring ZK proof system to financial institutions. And in this talk, I would like to introduce you to our open source new library called Paddle, a framework for exploring private auditable and distributed ledger specifically for financial institutions. And hopefully this talk we will see some relevant use cases and considerations that we make when we construct transaction schemes. Sorry. Play, I guess. Yeah, I just mentioned that, yes, Satanji should have been present in here and help me a bit with a walkthrough through the code, but he's watching, and later on we, of course, can interact and talk more. So I will start with just maybe a simple analogy that I have and I find maybe a bit funny but interesting to explain how important is privacy for financial institutions. And when my daughter was 3 years old, we would help her going to the toilet, dress up, and also doing everything we can for her. But at some point, she grew independent and decided to tell me, please give me some privacy. And the idea that she decided to have and try these tasks independently just because she wanted privacy was, I think, interesting moment to think that privacy enable the technology that we built, and ZK proof, of course, is improving all the time and hopefully would enable this technology of distribution of ledger that maybe later could even help distributing to more children when they're independent and you can do something else. So, of course, financial institutions are a bit older, but they also have the privacy as a great asset. But with privacy as a great asset, they also have the auditing aspect and the ability to minimize the risk of operation and therefore to get trust to all participants in transactions and trades. And the byproduct, of course, of having this auditing that maybe would be even remote and instant, that would allow not opening sensitive data and constantly maybe maintaining banks on a level of risk that could be operational. We also would be able to reduce settlements, overhead, and or maybe intermediates in payment systems that will allow us instant transaction closer to what we see on the public domain and cryptocurrency, but different. So in financial institution, we're not necessarily looking at decentralization of the problem, but maybe the distribution of the ledger to an encrypted ledger. And here I'm just looking at several considerations that might be slightly different from the popular transaction scheme that we see outside. One of the main considerations, and I've seen here that Blockstream is here, so they also looked at multi-asset, but for cryptocurrency. But in financial system, multi-assets is important, especially for when risk becomes relevant in the bond market, debit market. These are risks that needs to be taken in multi-asset fashion. So there is exchange, usually of cash and another asset. And also, maybe a bit counterintuitive is a trust. The trust, no trust setup or transparent or a transparent framework is necessary as a starting point. Because imagine you have independent regulators or auditors that are going to look at your ledger, then no trusted setup or transparent framework is actually necessary as a starting point. And of course, at some point, there will be added trust that will be relevant to the use case that we have. And then there will be maybe a quite complex privacy map. So we will be needed to accumulate different privacy requirements from each actor in a transaction. And maybe that's maybe related to the previous talks, that we need established cryptography. It means that we need to wait and see what the academy come up with. For example, if there are certain attacks or vulnerabilities that might be able. And it's positive to hear that Sigma protocols are still okay. So we are here to present Paddle, which is a framework to explore privacy and auditable distributed multi-asset ledger. And I'm here showing maybe the two popular versions outside for private auditable or private transactions that's verifiable on cryptocurrency, for example, Zeta for tokenization, and ZK Ledger for more related to financial institution, but doesn't deal with necessarily with confidential multi-assets or any implementation that would be relevant to smart contract. So in Paddle, we are looking maybe on a simple case where the data structure is very simple, is based on table, similar to actually to what ZK Ledger provide. But here we have 3 dimensions to the table. We will have the assets, which is confidential, and each row will contain several assets of transactions, and the columns will be the participants that are going to transact or observe the transaction. And you can see that what we see here is just a table, and that will make the construction of the transaction seem relatively simple, but of course it won't be scalable to a public solution like in fully decentralized system. However, we can still always deploy it on blockchain and be able to enjoy the benefit of validation of transaction and all the infrastructure of EVM type, but it will be constructed to the specific set of participants. And in this case, the set of participants is also the set of anonymity that we are desired to be play with. And here you see that the transaction scheme is based on Pedersen commitments as well as the signature to the public key of the participant. So this is also, we took it directly from what ZK Ledger proposed, but now we will change a bit of how the transaction scheme and what is a cell construct from. So if we have a Pedersen commitment that's initially perfectly hiding, but then when we have a signature of its randomness to the token, what we call the audit token, then it becomes computationally binding, but it allows us to be able to extract, if you have the secret key, the value of the hidden commitment. So this is very convenient if you then later want to disclose information or build your privacy map. And for that, we will show that a cell here is now consists of a commit token, some Sigma protocol proof of consistency to make sure that the randomness is binding, and it's the same in the commit, and the token correspond to the participant. And then we will have also complementary commit and complementary token, which are recommitting by other participants, and we will see how it looks like. But the idea is that the other participants are the ones that are going to provide proof of assets, which means that they're going to provide us the range proof that will tell us that there is no double spending or creation of assets. And we will see that the proof of equivalence is required now, because if another participant extracted the value from the commit, from the original commit of the broadcaster, then it will need also to provide some proof of equivalence to make sure that it's the same value. Again, those are Sigma protocols, and here proof of asset would be a range proof. Typically, or the best way to do that at the moment for now, for us, is using bullet proofs. And what we will see here now is a scheme of the multi-asset transaction. And on the right, I'm mentioning how it was, or how it looks like in ZK Ledger or Zeta type of transaction, where there is no interaction between the parties. But in the multi-asset, you will have extra round of communication. And I will try to justify why is it okay in the use cases for financial institution when you have multi-assets. So in the injective transaction, it's a simple case where you would, where the sender or the broadcaster will provide all the proof of asset for all the participants by knowing that he's going to debit its own account or on behalf of someone else, but the rest of the participants must have positive values. So it's only for debiting transaction, but in the multi-asset you can do whatever you want in terms of who is the input and the output of the transaction and who is debiting and crediting. So we can see here that you have the first round where the sender is going to just send the commit and tokens, which are the transaction input and output. And this is, of course, a homomorphic ledger, so this should sum to 1, or multiplication of the commitment should be 1, equals to 1. And that means that we are going to make sure that this is the balance of the assets. And now, for each participant, then they will be able to extract the value from the commit token, given that it was assigned to their public key. And once they can once they can extract their value, then they are able to provide the proof of asset, which will then will have another round of communication with the ledger to complete the full cell, and the full cell is then going to verification. So the idea is that you will have another round of communication to provide all the proof of asset from all participants, and therefore you will get cells that you cannot differentiate between each other. They all have the same structure, and according to the DDH, the combined system should hold. And you would then be able to prove the anonymity under this set of participants, and you will be able to generate concurrent range proof, and the most important, you will be able to exchange assets. And the idea behind it is that in most cases that we experience from, there will be anyway a round of communication in exchange of assets to make sure there is consent. So the ability to add in this consent also the proof of asset also as a signature then allow us to generate this relatively simple and general scheme for these use cases. In any case, we can always switch to the type of injective transaction. That's in the cost of having a bit more complexity on how we construct the Sigma protocol, but it's relatively straightforward if we look at ZK Ledger or Zeta. So I will try now to show a bit about how the auditing would look like. So now if we have a cell with commits and some proofs, then if we want an observer to be able to extract these values, we can always have another token and consistency proof to be able to make sure that this token is binding to the same commit, and then the observer be able to extract the same value. Now, this is very relevant to intermediate solution of settlement banking. So if a regulator mandates settlement banking, it means that even though that there's a ledger that is distributed and encrypted, it doesn't mean that the asset itself is going to transact in the ledger. So there will be always another step to make sure that the risk is regulated, and it's by another a bank that will be able to actually transact the asset behind the scene. And it can be after one record or many records, but the idea is that you can construct then the ledger in a very simple manner, that you will have just even the tokens from the commit that we have from the broadcaster between the two parties, and then the settlement bank token to be able to extract and make the trading, even without using the proof of asset. So this is relatively straightforward, but very useful practical case to bring ZK proof to financial use case. And now, when we have privacy preserving auditing, then we will look at maybe normal auditing that we will do on homomorphic ledger, for example, asset balance, average, etc. But now when we have confidential assets, then we can do also inter-assets auditing. And that quite easy to rearrange it to be able to provide ratio of the value. So we can do a kind of liquidity proof that relies on Sigma protocol on different two assets that belongs to a certain party. And we can do also rate. We can also prove rate of two transaction or two assets in a transaction. And that will allow us sometimes to also look at traceability, concentration of value in certain transaction or certain assets by proving rates. So these are relatively simple, and you can also look in our paper. And I want to have kind of a conclusive use case that hopefully will show you the reasoning behind this system is for the bond exchange and coupon rate use case. In this case, you will have the debit market where you have a bond issuer that would like to trade with this bond, and there will be some investors that coming in. And for these investors, there will be also maybe custodians and observer, like auditors that will look at this certain set of transactions. And the idea is that there is quite a complex map of what's the privacy requirement for that problem. So the custodian would want to see investor A that is going to operate according to its capital, and custodian B maybe to the investor B. And then the bond issuer would like to see to distribute coupon rate or interest rate after a year or two, but it wouldn't necessarily need to know what is the distribution of this coupon. And on top of that, you would have a broker that will get some fees and maybe will handle all this transaction. So there will be several requirements for the trust model and the privacy model in this setup. And simply we can generate the exchange bond in one transaction that contains two assets. And that also can include the custodian if needed in order to be observed using another token. And in addition, you can create even coupon rates that will prove that the coupon rate match the interest rate, for example, 10%, without letting even the bond issuer knows which investor gets how much. So that means that the investor will enjoy the privacy for how much they invested in the bond, and the bond issuer would not know the distribution of coupon. This is kind of one example that we see that you can imagine that in order to construct the privacy without ZK proof would be very problematic and complex, but with ZK proof it can be a very simple ledger after all. Yes, so I think that's from the case of the use cases, and I just want in the last slide to introduce you to the link for the library, and this is an open source library that you can and I'm inviting you to maybe even contribute and maybe see where potential we can include more use cases. And here I'm showing a simple example that's how the performance is going. The idea is that this library is based on Rust implementation of the cryptography primitives. So we're looking at two curves that we implemented, the BN254 and SEX256. They actually relies on style implementation that already existing before, as you might know, bulletproofs and then GoX for the protocols and for the primitives, and bulletproofs is for the generation of the proof. And then on top of that, we created several Sigma protocol in Rust, and later we have an interface to Python for this Rust. So the performance is maintained, and the most maybe relevant fact is that we also have interaction with smart contracts, and also another implementation of bulletproof verification if you would like to see. So all of that is in here, and hope you will visit, and also the paper is linked in this link. So happy to discuss later, and thank you for your attention.
Thank you. Thank you so much for this presentation. If I will ask people that have follow-up questions to go catch you directly,
Yeah, definitely.
if possible.